Hi, I'm Jessica Baudet. I'll be talking about characterizing sub-terahertz MIMO channels in practice, a novel channel sounder with an absolute timing reference that I developed with my team. Over the past several decades, there's been a steady increase in the number of devices that are connected wirelessly, and this increase has led to a lot of congestion in the lower frequency bands and a push to use higher frequency bands like millimeter wave, sub-terahertz, and the terahertz band for communications. The terahertz and sub-terahertz band are especially exciting because they have broad windows of available bandwidth that will enable data rates of up to 1 terabit per second links without some of the challenges that you would face going up all the way up to optical systems. These broad windows of bandwidth aren't the only ways we're going to reach our 1 terabit per second link though. In this plot, we're showing how much bandwidth you would need for a given number of MIMO channels, a given modulation order. So for example, if we are using 2 MIMO channels, we would need modulation orders of 1024 QAM and bandwidths of 50 gigahertz to hit our 1 terabit per second link. That's kind of problematic because first of all, there's no continuous 50 gigahertz spectrum available for use in communications without any restrictions. And second of all, there's too much noise in 50 gigahertz of bandwidth to support 1024 modulation orders. So we're definitely going to need modulation MIMO channels. We're also definitely going to need more than 2 MIMO channels. But to build sub-terahertz MIMO channels, we're going to need a reliable sub-terahertz MIMO channel model. And there's been a lot of theoretical models that have been presented in literature, which is really great. But ideally, we're able to verify these theoretical models with experimental models. But the problem is there aren't that many experimental platforms that are able to reliably characterize a sub-terahertz or terahertz MIMO channel. Of the few that have been presented, they fall into 2 categories. The first is the vector network analyzer based channel sounders, and these require a cable to connect the transmitter and the receiver, so that limits the distances that we can practically experiment with. And they are also unable to characterize time-varying broadband channels. On the other hand, people have used correlation-based channel sounders, and they don't require the cable. They can measure broadband time-varying channels, but if they don't have a time reference, which they haven't in the past, they're not able to distinguish multipath components from line-of-sight components. And that is a big hindrance into the reliability of the channel sounder. So in our channel sounder, we add an additional transmit receiver link at a separate frequency to give us that timing reference in a correlation-based channel sounder. And so in this way, we're able to measure broadband time varying effects. We're not distance limited, and we have the ability to distinguish line of sight from multipath components. And using this channel sounder, we're able to measure a lot of different metrics, including the K factor, which tells us how close our channel is to a line of sight path. We measure the condition number, which tells us how well our channel can support multiple data streams. The SNR path loss, which tells us how strong the channel will be at the receiver, or the signal will be at the receiver. And we can also measure the capacity, which would be the ideal upper bound for the data rates our channel can support. And we show some preliminary results of these data rates, of these metrics in our paper. But the real win here is that we have an experimental platform that allows us to verify and inform our theoretical models that we can use to design future sub-terahertz MIMO communication systems.